Good morning everybody. I am Dr. Rajini Samuel, Associate Professor of Biochemistry, Shri Sathya Medical College and Research Institute, Chennai, India. My research topic is Novel Graphical ABG Interpretation Method. Introduction and aim. The technological development in the blood gas analyzer that has happened in the last few decades has not resulted in corresponding development in the field of diagnosis. A new graphical tool was developed by myself for ABG interpretation, representing various acid-base disturbances in a 4-quadrant graph method. Arterial blood gas analysis. The measured parameters like pH, PCO2 and calculated parameters like bicarbonate and standard base excess are routinely utilized for ABG interpretation. The parameter PCO2 denotes the respiratory component. The bicarbonate and standard base excess represents the metabolic component in physiological and base excess approach respectively. Bicarbonate concentration is a variable parameter because it varies with the changes in PCO2 values. As PCO2 increases, it reacts with water molecules to form carbonic acid. This reaction is catalyzed by the enzyme carbonic anhydrase present inside red blood cells. Carbonic acid dissociates into hydrogen and bicarbonate ions. The liberated hydrogen ions are buffered by non-bicarbonate buffers like hemoglobin, albumin and phosphate. The concentration of bicarbonate increases with increase in PCO2 and decreases with decrease in PCO2 values. This problem of respiratory influence in causing alterations in bicarbonate concentration is solved by the measurement of standard bicarbonate. Standard bicarbonate is the concentration of bicarbonate in the plasma from blood, which is equilibrated with a normal PCO2 of 40 mmHg and normal PO2 100 mmHg at a normal temperature 37 degrees Celsius. Deviation under respiratory influence. The actual bicarbonate and the standard bicarbonate concentrations are approximately equal under normal ventilation. But in hypoventilation and hyperventilation, the two values differ and deviate from each other. The ratio and the difference will deviate in abnormal ventilation depending on the changes in the concentration of PCO2. So using this concept, some novel ratios are derived. Carbonic acid concentration derived from PCO2 using the relationship H2CO3 is equal to 0.03 into PCO2. The ratio 1 denotes the ratio between bicarbonate carbonic acid and standard bicarbonate carbonic acid ratios, which is numerically the same as the ratio between bicarbonate and standard bicarbonate value. So ratio 1 is equal to bicarbonate divided by standard bicarbonate. Ratio 2 denotes the difference between bicarbonate carbonic acid and standard bicarbonate carbonic acid ratio. So ratio 2 is equal to bicarbonate minus standard bicarbonate divided by carbonic acid. In the graph 1, PCO2 is related with ratio 1. As PCO2 increases, ratio 1 also increases. Ratio 1 is the ratio between bicarbonate and standard bicarbonate. At PCO2 40 mm of mercury, the ratio 1 is 1 because both bicarbonate and standard bicarbonate values equal. So ratio is 1 at PCO2 of 40. In the graph 2, the relation between PCO2 and ratio 2 is clearly shown. As PCO2 increases, the ratio 2 also increases and the value is greater positive for PCO2 more than 40 and the values are negative for PCO2 lesser than 40. So ratio 2 is equal to bicarbonate minus standard bicarbonate divided by carbonic acid. As PCO2 increases, bicarbonate concentration also increases. So the difference between the bicarbonate and standard bicarbonate will increase towards positive side. So the ratio is positive for increased PCO2 and negative for decreased PCO2. The relationship between PCO2 and the ratio between bicarbonate and standard bicarbonate depicted in the graph 1 clearly shows that as the PCO2 increases, the ratio 1 also increases, and afterwards the curve slightly flattens. The ratio 1 values are greater than 1 for increased PCO2 and lesser than 1 for decreased PCO2 values. Similarly, the ratio 2 is greater positive for increased PCO2 and greater negative for decreased PCO2 values. At PCO2 40, both bicarbonate and standard bicarbonate values are equal. So the difference is 0. Obviously, the value of ratio 2 is 0 if the ratio 1 value is 1. Because at PCO2 40, both bicarbonate and standard bicarbonate value is equal. So the ratio will be 1, but the difference will be 0. The correlation between PCO2 and the ratio 2 depicted in the graph 2 clearly shows that as the PCO2 increases, the ratio 2 also increases, and afterwards the curve flattens. But this flattening is reduced and the curve is slightly steeper if ratio 3 is utilized. Ratio 3 is obtained by multiplying ratio 2 with ratio 1, which are clearly shown in the graph 3. In the graph 3, relation between PCO2 and ratio 3 is clearly shown. Ratio 3 is obtained by multiplying ratio 1 with ratio 2. So ratio 3 is similar to ratio 2. It is greater positive for increased PCO2 values and greater negative for decreased PCO2 values. So application of these newly derived ratios. In respiratory acidosis due to hypoventilation, PCO2 retention occurs, and in respiratory alkalosis due to hyperventilation, PCO2 value is decreased. These ratios are greatly altered in respiratory disorders and also in metabolic acid-base disturbances associated with respiratory compensations. The alteration of ratio values are minimal in purely metabolic acid-base disturbances without respiratory compensation. The normal ratios derived using actual bicarbonate, standard bicarbonate, and carbonic acid values render some clues in discriminating various acid-base disturbances. Next, we will discuss about modified Henderson equation. H plus is equal to 24 into PCO2 divided by bicarbonate. The concentration of bicarbonate is calculated using this modified Henderson equation in the ABG analyzer. pH is equal to 9 minus log of H plus. pH can be calculated from the hydrogen ion concentration. The measured pH is not directly related to the individual values of bicarbonate and PCO2 values, but it depends only on the ratio. Measured pH depends only on the ratio between bicarbonate and carbonic acid. Non-respiratory hydrogen ion concentration. The calculated hydrogen concentration equivalent of standard bicarbonate is called the non-respiratory hydrogen ion concentration, NRH plus, hydrogen ion concentration at non-respiratory pH. So this is PCO2 of 40 millimeter of mercury. So using the same modified Henderson equation, 24 into PCO2 divided by bicarbonate, you have to substitute for standard bicarbonate. So NRH plus is equal to 24 into PCO2 divided by standard bicarbonate, and in the place of PCO2 you have to substitute 40. NRH plus is equal to 24 into 40 divided by standard bicarbonate. So NRH plus is equal to 960 divided by standard bicarbonate. NRPH is equal to 9 minus log of NRH plus. NRH plus is equal to 960 divided by standard bicarbonate. NRPH is equal to 9 minus log of NRH plus. Non-respiratory hydrogen ion concentration. The relation between NRH plus and standard bicarbonate shown in the graph 4 clearly depicts the shape of the graph is rectangular hyperbola, and as non-respiratory hydrogen ion concentration increases, the standard bicarbonate decreases and vice versa. The relation between non-respiratory pH and standard bicarbonate shown in the graph 5 clearly depicts that as the non-respiratory pH NRPH increases, the standard bicarbonate also increases, and vice versa. So in the graph 4, the relation between standard bicarbonate and NRH plus non-respiratory hydrogen concentration is clearly shown. So as the standard bicarbonate increases, NRH plus decreases. In the graph 5, the relation between standard bicarbonate and NRPH is clearly shown. NRPH is calculated by 9 minus log of NRH plus relationship. So as the NRPH increases, the standard bicarbonate also increases. So using this concept, a novel ABG interpretation method can be developed. The net changes in total pH or actual pH includes both the changes in respiratory and non-respiratory component affecting the pH. So the relationship is delta pH is equal to delta RPH plus delta NRPH. A novel ABG interpretation method is developed correlating the net changes in total or actual pH with the changes in respiratory and non-respiratory component affecting the pH. So net changes in total pH. So delta pH is equal to delta RPH plus delta NRPH. Delta pH is equal to pH minus 7.4. This denotes the net changes in total or actual pH. Actually 7.4 is the pH at which the hydrogen concentration is 40 nanomoles per liter. Delta NRPH is equal to NRPH minus 7.4. This denotes the changes due to non-respiratory component. And delta RPH is equal to, we have to subtract delta NRPH from total change. So delta RPH is equal to pH minus NRPH. This denotes the changes due to respiratory component. Some examples are shown. pH 7.37. So delta pH is pH minus 7.4. So 7.37 minus 7.4 will be getting minus 0.03. And using derived formulas, we can calculate delta RPH and delta NRPH. So if you look at that, delta pH is due to both the delta RPH and delta NRPH. If you look at the other example, pH 7.4, the delta pH is 0 because pH minus 7.4 is 0, and changes is due to both respiratory and non-respiratory, but both are acting in opposite. The delta RPH is minus 0.170. The delta NRPH is 0.170. So both are equal but opposite. So the net change is 0. So this concept can be applied for any ABG report. Derivation of delta RPH calculation. So pH is equal to 9 minus log of H plus. NRPH is equal to 9 minus log of NRH plus. So pH minus NRPH is equal to minus log of H plus divided by NRH plus. Or pH is equal minus NRPH is equal to log of NRH plus divided by H plus. So H plus can be calculated using the modified Henderson equation, 24 into PCO divided by bicarbonate, and NRH plus can be calculated using the same modified Henderson equation, but you have to substitute. In the place of PCO you have to substitute 40, and in the place of bicarbonate you have to substitute standard bicarbonate. So NRH plus is equal to 24 into 40 divided by standard bicarbonate. Calculation of NRH plus divided by H plus. So NRH plus divided by H plus is equal to 40 into bicarbonate divided by standard bicarbonate divided by PCO2. So we have to substitute in the above relationship. We will get the following relation: pH minus NRPH is equal to log of 40 plus log of bicarbonate divided by standard bicarbonate minus log of PCO2, or pH minus NRPH is equal to 1.6 plus log of bicarbonate divided by standard bicarbonate divided by PCO2. In the graph 6, the relation between PCO2 and delta RPH is clearly shown. Delta RPH values are negative for increased PCO2 and positive for decreased PCO2. So pH minus NRPH is equal to 1.6 plus log of bicarbonate divided by standard bicarbonate divided by PCO2. At PCO2 40, pH minus NRPH is 0, because already we discussed about ratio 1. The ratio between bicarbonate and standard bicarbonate is 1 at PCO2 40, because both bicarbonate and standard bicarbonate values are equal. So log 1 is 0 and log 40 is 1.6. If you substitute, we will be getting 0. It is very clear that delta RPH value is negative for increased PCO2 and positive for decreased PCO2 values, which are clearly shown in the graph 6. So the respiratory component delta RPH, pH minus NRPH, the magnitude and direction denotes whether it is towards positive side or towards negative side. The magnitude and direction of the changes in the parameter delta RPH denotes the respiratory influence in causing changes in pH. If the value is more than 1 or pH minus NRPH is positive, it denotes alkaline effect, and if the value is lesser than 1 or pH minus NRPH is negative, then it denotes an acidic effect. Metabolic component NRPH minus 7.4. High non-respiratory pH is seen in metabolic alkalosis, which is related to a higher value of base excess. So base excess already discussed. It is one of the metabolic component. The normal base excess value, standard base excess value is from -2 to +2 millimole per liter. If the value is more than 2, it denotes metabolic alkalosis, and if the value is less than -2, it denotes metabolic acidosis. So high non-respiratory pH is related to more positive value of base excess, and base deficit or lower or more negative value of base excess is related to low non-respiratory pH, which is seen in metabolic acidosis cases. So high non-respiratory pH is seen in metabolic alkalosis, and low non-respiratory pH is seen in metabolic acidosis cases. The relationship between standard base excess and the metabolic component NRPH minus 7.4 is clearly shown in the next graph. So graph 7 shows the relation between standard base excess and NRPH minus 7.4. So NRPH minus 7.4 nothing but delta NRPH. So it is positive. When the base excess values are positive, the delta NRPH is also positive. When the base excess values are negative, NRPH minus 7.4 value is also negative. So both are well correlated. Novel ABG interpretation method. From the normal reference level of pH, the normal level of delta pH is calculated as plus or minus 0.05. So normal arterial blood pH is from 7.35 to 7.45. So delta pH is pH minus 7.4. So using this relationship, the normal delta pH is calculated as from minus 0.05 to plus 0.05. If the delta pH is less than minus 0.05, it denotes acidic pH, and if the delta pH is more than plus 0.05, it denotes alkaline pH. Then the value of delta pH is compared with the values of delta RPH and delta NRPH, because we already discussed the delta pH is equal to delta RPH plus delta NRPH. So delta RPH is more negative for respiratory acidosis and more positive for respiratory alkalosis. Delta RPH is the respiratory component. If it is more negative, it denotes respiratory acidosis, and if it is more positive, it denotes respiratory alkalosis. Similarly, delta NRPH is a metabolic component. If it is more negative, it denotes metabolic acidosis, and more positive denotes metabolic alkalosis. If changes in both the components are involved, it may denote a combined acid-base disturbances. Either it can denote a compensating mechanisms or mixed acid-base disorders. If the changes in pH due to metabolic and respiratory component are equal but opposite, then the net change is 0 because it is cancelled out each other. So one of the example I showed you, pH is 7.4, delta pH will be another 0 because on 7.4 minus 7.4 is 0 because both the metabolic and respiratory component are equal in magnitude but the direction is opposite. One will be in plus sign, other will be in minus sign. So the net change is 0. Few examples are shown in the table. So this concept can be applied for any ABG interpretation. So usually in ABG interpretation, we will be looking at the pH, whether it is normal or it is towards acidic or towards alkaline. Then we have to find the cause for acidic or alkaline. We will be looking at the metabolic component, either bicarbonate or standard base excess, and we will be looking at the PCO2 for the respiratory component. Based on this, we will classify the acid-base disorders, whether it is simple or any compensating mechanisms takes place or mixed disorders. In this novel interpretation method, just we have to look at only the pH change. First we look at the pH and then delta pH. Delta pH is nothing but pH minus 7.4. We have to compare pH minus 7.4 with delta RPH and delta NRPH. So using this concept, we can classify the various acid-base disorders because delta RPH is well correlated with PCO2. I already showed in the graph. Similarly, delta NRPH is well correlated with standard base excess. So routinely, standard base excess we are using for metabolic acid-base disturbances. So delta NRPH is well correlated with standard base excess and delta RPH is well correlated with PCO2. So this interpretation method can be applied. If you consider the first example, pH is 7.45, the change in pH minus 7.4 is 0.05. Then you look at the delta RPH and delta NRPH. Delta RPH is 0.022, delta NRPH is 0.028. So delta pH is due to sum of the delta RPH and delta NRPH. If you look at this other example, serial number 3, pH is 7.27. The delta pH minus 7.4 is minus 0.13. This is due to changes of both delta RPH and delta NRPH. So you compare minus 0.13 with delta RPH and delta NRPH. Here delta RPH is minus 0.251. Delta NRPH is 0.121. So delta RPH is correlated with delta pH. So the acidic pH is due to the respiratory component. Then why the delta NRPH is changed? Because of compensations. So this concept can be applied for any ABG disorders. Delta RPH is more negative for respiratory acidosis, more positive for respiratory alkalosis. Similarly, delta NRPH is more negative for metabolic acidosis and more positive for metabolic alkalosis. So using this, we can classify the acid-base disorders into normal respiratory acidosis, respiratory alkalosis, metabolic acidosis, and metabolic alkalosis, and even the compensations will be seen as a change in the other component. Suppose if both the components are involved, then it denotes compensatory or mixed disorders. So various acid-base disorder groups, a total of 250 arterial blood gas sample data were utilized and classified into various acid-base disorders based on their normal ranges. The normal reference for arterial blood pH is from 7.35 to 7.45, for PCO2 is from 35 to 45, and for bicarbonate is 22 to 26 milliequivalent per liter. The various groups are tabulated in the tables 2, 3 and 4. So normal cases, respiratory acidosis again classified into respiratory acidosis 1, 2, 3 based on the PCO2 values, and respiratory alkalosis again classified into subgroups 1, 2, 3, 4 based on the PCO2 values. Metabolic acidosis and metabolic alkalosis, they are again classified into subgroups based on the bicarbonate values. And miscellaneous cases 1, 2, 3 are also shown in the table 4. So using this concept, we can construct a novel 4-quadrant graph. A novel 4-quadrant graphical tool was developed by myself for ABG interpretation using standard base X's in the x-axis and the ratio 2 or ratio 3 values in the y-axis. Various acid-base disturbances can be analyzed in a graphical method. Standard base X's is taken in the x-axis. The normal values are -2 to +2. More than +2 denotes metabolic alkalosis and less than -2 denotes metabolic acidosis. This is taken in the x-axis, and ratio 2 and ratio 3 will be greater positive for increased PCO2 and greater negative for decreased PCO2. So normal range for standard base X is from plus or minus 2 millimole per liter. Value more than +2 denotes metabolic alkalosis, and value less than -2 denotes metabolic acidosis or base deficit. The acid-base disorders can be classified and plotted in the 4-quadrant graph. Each acid-base disorders will occupy any of the 4 quadrants, and the normal arterial blood gas analysis reports will be seen around the center of the graph, which are clearly shown in the table 5 and graph 8. So in the first quadrant, both the x-axis and y-axis are positive. So both metabolic alkalosis and respiratory acidosis are seen. In the second quadrant, x-axis positive and y-axis negative. So metabolic alkalosis and respiratory alkalosis are seen. In the third quadrant, both the x-axis and y-axis are negative. So metabolic acidosis and respiratory alkalosis are seen. In the fourth quadrant, x-axis negative and y-axis positive. Metabolic acidosis and respiratory acidosis are seen. Normal cases are seen around the center of the graph. Simple acid-base disorders are represented by plots. The plots will be towards single axis, either x-axis or y-axis. The combined acid-base disturbances, compensatory mechanisms, or mixed acid-base disorders, the plots will be seen in between x-axis and y-axis. So for simple acid-base disorders, plots will be towards any single axis, and in combined acid-base disturbances, plots will be seen in between them. And the graph 8, in the x-axis standard base X's value is taken, and y-axis ratios 3 is taken. First quadrant, second quadrant, third quadrant, and fourth quadrant are clearly marked in the graph. So standard base X's is taken in the x-axis. Normal values from -2 to +2, more than +2 metabolic alkalosis, less than -2 metabolic acidosis. The ratio 3 will be positive for greater positive for increased PCO2. So positive for respiratory acidosis and negative for respiratory alkalosis. So all the 250 cases are divided into various groups. All are plotted. So easily you can plot in the 4-quadrant graph method. So rectification, a minor drawback of this graph tool is it may not clearly demarcate the different higher levels of PCO2 values, but this can be corrected in the 3-dimensional graph if PCO2 values are included in the third axis. The 3-dimensional graph, the parameter PCO2 minus 40 mm of mercury should be taken in the third axis, because the ratio bicarbonate minus standard bicarbonate divided by carbonic acid is 0 at PCO2 40. At PCO2 40, both bicarbonate and standard bicarbonate value is equal. So the difference will be 0. So the central point will be 0. A graphical tool constructed using standard base X in the x-axis and the parameter PCO2 minus 40 in the y-axis clearly shown in the graph 9. 3-dimensional graph can be constructed by merging the two graphs 8 and 9. So in the graph 9, standard base X is taken in the x-axis, PCO2 minus 40 is taken in the y-axis. So PCO2 minus 40, normal PCO2 is from 35 to 45. So increased PCO2, the positive values will be seen for respiratory acidosis and negative values will be seen for respiratory alkalosis. 4-quadrant graph for the novel ABG interpretation method. A similar 4-quadrant graph method can be constructed using the parameters delta NRPH in the x-axis and negative of delta RPH in the y-axis. So already we discussed delta NRPH is similar to the standard base excess. This value is more negative for metabolic acidosis and more positive for metabolic alkalosis. And value of delta RPH is more negative for respiratory acidosis and more positive for respiratory alkalosis. So this is opposite to ratio 2 and ratio 3. So we have taken negative value of delta RPH. If you take negative value, it will be similar to the ratio 2 and ratio 3. So negative value of delta RPH will be positive for respiratory acidosis and more negative for respiratory alkalosis. So in the x-axis, delta NRPH is taken, the metabolic component is taken, and the y-axis, negative value of delta RPH, respiratory component is taken. So easily, the various acid-base disorders can be plotted in the 4-quadrant. Conclusion: the arterial blood gas interpretation plays a vital role in emergency clinical conditions, yet it remains a challenging task. This novel arterial blood gas interpretation appears to be easier and simpler and may serve as a supporting tool for better understanding and quicker interpretation of ABG reports. This recently proposed graphical tool by the current author may fulfill the requirements for a graphical visualization method to be applied in clinical practice. And these are the references taken. Last but not the least, I would like to thank all the organizing committee members for giving me an opportunity to present in this forum of learned scholars so that this research work can be further carried out and analyzed for a fruitful outcome. Thanks to my university and chairperson for helping me to complete this research work. Thank you.